Okay, so here's our single slit. Alright, here's our single slit. Here comes the light. It's going to diffract. Different angles, right? So we're going to take a beam. We're going to look at, watch what it does. So let's say this one travels a distance A. Now let's take one at the middle. Okay, so we'll take one at the middle. This one's going to travel a distance of A plus a wavelength. So it's traveling a little bit farther. It's going to travel distance A plus a wavelength. Okay, let's look at another one. This one right here. Okay, what's this one going to travel? Okay. How about if we go in between here? What's this one going to travel? What about this one over here? Okay, so what we're going to do is we're going to look at a few beams of light and see how they interact with each other. For example, if we take this A and this A plus a half, what's going to happen with these two? This one right here, okay, this one and this one, what are they going to do with each other? They're going to destroy each other. So this plus this is going to destroy each other, right? Because a half wavelength difference. What about this A plus a half plus A plus a full? What are those two going to do? Destroy each other. What about this A plus a full and this A plus 3 halves? Destroy. What about this A plus 3 halves and this A plus 2? Destroy. So if we did it with each little individual beam everywhere, what are they going to do to each other? Destroy. So you can think of the first half of the beam is going to cancel out with the second half of the beam. So what should you expect over here? Okay, so you should expect a dark spot right there. Okay. Could we do it with another set of beams? What's going to happen right down the middle? Well, right down the middle, you're going to clearly get a bunch of bright spots. They're all going to interfere constructively. Okay, what about, is there another one we could construct and create this?
On the other side of the bright spot.
On the other side of the bright spot. What do you think the path difference is going to be that time?
Same but negative. The bottom.
So what if we drew one like this? So that this was A, this is A plus a half, and this is A plus a full. So let's do it again. What's going to happen with A and A plus a half? It's going to cancel out. What's going to happen with a teeny bit farther than A plus a teeny bit farther than A plus a half? What's going to happen with the A plus a little bit farther and an A plus a little bit farther plus a half? It's going to cancel. So in other words, the first half of this is going to essentially cancel with the second half of this. What should you expect over here? A dark spot. So if we go back here, that second one that I drew, where's that going to be in comparison to that first one that I drew? Is it going to be below it or above it?
Below.
Below it. Why is it going to be below it?
Because instead of a plus lambda, just a plus 1/2 lambda.
Good. So the ultimate path difference, and when we talk about path differences with single slits, we're talking about the very first one with the very last one. So what's the path difference ultimately with this one?
Lambda.
Lambda. What was the path difference with this one?
2 lambda.
2 lambda. If I did another one, could you tell me what it's going to be? 3 lambda, and so forth, right? So that this would be our first order dark spots. Okay, first dark, second dark, third dark. And then we have this bright spot right here. Now the equations we use are going to be exactly the same, except instead of the distance between the slits, we're going to define D as the width of the slit. And actually a lot of times you'll just see that written as W for width. But just to keep our equations the same, we'll just call it D. Now the equations are going to be the same. So what are the equations again, just so we have them right in front of us? Okay, and if we do the approximation, so these apply here as well. I do want you to notice the m is different. For m equals 1, 2, 3, what does that tell us? That tells us the dark spots. So for a path difference of 1 lambda, 2 lambda, 3 lambda, that's going to produce a dark spot. So let's see what happens for our bright spots. Okay, notice this is my first bright spot right here. Where does the first bright spot end? At the first dark spot. So the first bright spot will end at the first dark spot. Okay, so let's look at where, I said first, we should say what the 0 is. The central, usually for single slits they call it the central bright spot. So the central bright spot is going to be end at the first dark spot. So let's look at how we get our first order bright spots. And this one's a little bit confusing. I'm going to draw one more. If you have space on yours, you could draw it on it. Alright, so we're going to take a look at this one. Okay, so what do we call these? A. Alright, so I'm going to do A. I'm going to do A plus a half. I'm going to do A plus a full. And the last one is going to be A plus 3 halves. Okay. Alright, so we're just going to go through. We're going to look at these beams. So what's A plus a half going to do? Cancel out, right? And A plus a half is going to cancel. What's A plus a little bit and A plus a little bit plus a half? Cancel. A plus a little bit more, A plus a little bit more plus a half, what's it going to do? Cancel. So in other words, this first third is going to cancel out with this second third. So the first third of the beam is going to cancel out with the second third of the beam. These have now canceled each other out. This last third has nothing to cancel out with. So what happens? It's just there. So that's going to be our, what we would call our maximum or our bright spot is going to be, well, what's the ultimate path difference here? So this would be the first bright. What's the path difference between the first and the last?
3 halves.
3 halves. So I'll write this as PD 3 halves, or M equals 3 halves. All right? So without doing it, can you predict where the second bright's going to be?
5 halves.
5 halves, yeah.
Then 7 halves.
So that's going to be 5 halves, and so forth and so on. All right? So if we were to then summarize, the equations are going to be the same. What's our M's going to be for bright?
The halves.
For, M brights for the single slit.
0.
1 half.
Okay, so the very first one would be 0, just because it's the central bright spot. Where does the first bright spot occur then?
3 halves.
3 halves, good. So this is what always gets people, because what do you want to think it's going to be? 1 half, okay? But the first one happens at 3 halves. And one of the ways you can think about how 1 half is impossible is because, go back to your picture, the first bright spot doesn't end until, what's the path difference? 1 whole wavelength. So where would, if you thought it was 1 half, where would that 1 half be?
It's like a half.
It would be right here, which is already a bright spot itself. So the first bright spot does not end until you've reached the first dark spot. So the next bright spot can't begin until after the first dark spot.
So is the distance of the 0th bright spot, or the length of it, the length of the slit? The whole thing?
No, and that's a good question. It's not necessarily going to be the width of the slit. In fact,
Would it be
as
longer?
this is the width of the slit, and this is a good conceptual question, as the width of the slit gets smaller, what should happen to the size of the 0th bright spot? It should get wider, bigger, yeah. So it's an inverse relationship. So as this gets smaller and smaller, this is going to actually spread out. Yeah.
Is the brightness like universal in the 0th? Correct? The 0th bright spot?
No, it would decrease. So it would peak right in the very middle, and then it's going to decrease. And actually, that brings up a good question. How should this brightness compare to the central brightness? Remember we said before that all the brightnesses were relatively the same, right, over here? All across, they're about the same. How should this one be, though? Should it still be the same? Should it be more? Should it be less? It should definitely be less, because to get this bright spot, what did we do? We canceled out 2/3 of the beam, right? So we canceled out 2/3 of the beam. We're only left with 1/3. So it should be much dimmer, in fact about 1/3 dimmer, all these other bright spots. Okay, so let's go back to this. Remember I told you to leave a space.